All right, today we are finally starting logarithms, which many of you saw in your CDTs, the word log. We're going to find out what those are today. So we've talked about functions in the past, like y equals x squared and y equals plus or minus the square root of x. Those are considered inverse functions, right? Remember, to find an inverse function, we would switch the y and the x variable, and then we would solve for the other letter. Or we would graph the original and then reflect it about the line y equals x. Remember, we could do that graphically or algebraically.
Are you busy?
Yeah, teaching us.
When you done? It's not good for me.
Sorry. Who's that person? That was Jesse. He's in my next period class. Okay. So today we're going to look at inverse functions, but we'll be looking at the inverse of an exponential function. So we've seen exponential functions. Now instead of a times b to the x, we'll just be looking at b to the x. We're going to find out that its inverse is a logarithm. Okay, the inverse of this would be log base b. Okay, so it's a little subscript of b, log base b of y equals x. These are considered inverses. Okay, so a big part of today's lesson is just going to be writing logarithmic expressions, converting from an exponential to a logarithmic back to an exponential, and there's a little pattern. And then we're also going to graph logarithmic functions by using the inverse identity. So the warm-ups just ask us to identify which value of x would make this equation true. So for number 1, if 8 equals x cubed, what is x? 2. Cube root both sides, or just mentally think what cubed gets me 8. How about number 2? What would we have to do to both sides to solve for x? Yes, we are going to multiply the exponent by a reciprocal. So this would be raising them both to the 4/1 power, which would get me x equals 2 to the 4th is 16. Now the next one, this is kind of what we're going to run into today. To solve this, you would take the x root. Like, what is the x root if you don't know what type of root you're taking? So really you're just going to think, what number, if I plug in here, will get me 27? So like 3 to the second is 9, 3 to the third is 27. Therefore, x has to be 3. Okay, so a little bit of just mental math. The last one, what do you think the value of x would be to make those two sides equivalent? Evan?
2.
Good. Again, the exponents would have to be equivalent, so 6 would have to be equal to 3x, and then when we divide both sides by 3, we would get 2. So here's the definition of a logarithm. A logarithm to the base b of a positive number y is defined as the following. Now, what you'll notice between this is considered exponential form, y equals b to the x. This is considered logarithmic form, log base b of y equals x. Now, one thing you're going to notice is that the base of the exponent and the base of the logarithm, those stay the same. You can see down here, they're not all going to have variables. They're going to have numbers and variables in them. But the base of the exponent is also the base of the logarithm. So those stay the same. But you'll notice that the variables like switch where they're located. So like b had x with it. When it does the logarithm, b will have y with it. So kind of like because they're inverses, that they switch their two letters, x and y, around. But the big thing to keep the same, again, is that our base of the exponent is going to stay the base of the logarithm. And you'll also notice that it says that b has to be, you're finding the positive number y, so you do want this number to be a positive. We'll take a look on the back why it can't be negative when we see the graph of this logarithm. But let's jump into some examples with numbers. So the first set of directions ask us to write each equation in exponential form. So we're going to convert from logarithmic form back to exponential form. So remember, the base of the logarithm has to stay the base of the exponent. So this would be 5 to some power. Now, when you choose what power you're raising it to, it is going to be the number on the opposite side. So it'll be 5 to the third power, then you'll bring down your equal sign, and then it'll be equal to what we were taking the log of, which is 125. Does that make sense? 5 cubed equals 125? Yes. Also, you'll notice that it's kind of a counterclockwise rotation in terms of how the numbers go. So we have the base to the other side's exponent is equal to what we were taking the log of. So for anyone visual, that may help you. So the next one, the base of the log is 2. So the base of the exponent is 2. And we'll raise that to the fourth power, and that's equal to 16. 2 to the fourth is 16. Keep going, we have log base 3, so this would be 3 to the fifth equals 243. And 6 to the second power equals 36. Now the directions switch and we're going to go backwards. I'm going to give you the exponential form and I want you to work backwards to give me the logarithmic form. So again, the big thing is the base is still the base. So the base of the exponential form is now the base of the logarithm, and that is like a subscript, like a little small number underneath the log. So this is pronounced log base 2. Now is it going to be of 5 or of 32? Of 32. Very good. The other side, they flip-flop kind of, just like an inverse would, equals 5. Now, check it. You can always check logarithmic. 2 to the fifth equals 32. Using your little rotation, you can see that it would get you back to your exponential form. So the next one, the base is 3. So this would be a log base 3 of the big number, 729, equals 6, equals the exponent. Now fractions don't change anything. You can have a log with a fractional base. So this is still the base 1/2. So this would be log base 1/2 of 1/8 equals 3. So that's 1/2 to the third power equals 1/8, which would be true. And the last one would be what? Bless you. Log base 10 of 1 equals 0. Just be careful because this is not an exponent, this is a base. And it looks like 10 to the first. But it would be log base 10 of 1 equals 0. And again, check that, 10 to the 0 equals 1. Now, down here, they're going to change the directions and they ask us to evaluate each logarithm. So when you evaluate, normally you plug numbers in and then you simplify down to get an answer. So they really want us to tell them what is the answer to this. What's the numerical answer? Now, some of you on your CDTs may have noticed on the calculator there is a log button. Okay, now the log button only works if it is a base 10. Why? They don't have a special feature for you to change the base. Okay, they have, and we'll talk about this on the back, this is called the common log, which is a log base 10, they just don't write the 10. So any of these, even though it says without a calculator, you literally can't do them in a calculator right now. I will teach you a formula later that will help you to change the base to a 10 base, but until you learn that formula, you actually can't use the calculator. So we'll have to do these by hand. Now, before we get started, I have 2 typos. This should be log base 32 instead of 64. And this should be log base 9 of 3. I thought I changed those, but apparently I didn't hit save. For printers. All right, so we're asked to find what is this value. So what you're going to do is you're going to set this up as an equation with a variable on the other side because we want to find out what it's equal to. So log base 3 of 81 equals x. Then we're going to change to exponential. So we'll change this to exponential form, remembering the base of the logarithm stays the base. So this will be 3 to the x power equals 81. And then this is like the bell ringer, or the warm-up question on the top. You have to ask yourself, 3 to what power gets me 81? What number can I plug in for x that would make this true? Okay. Again, this is kind of trial and error. 3 to the second is 9, 3 to the third is 27, 3 to the fourth is 81. So my answer is 4. Now, if you want to put x equals 4, that's okay. Really, though, the answer is just 4. We added the x into the problem, so you don't need that as part of your answer. Okay, the next one, same thing. Set it equal to some variable. We'll just usually use x. Change to exponential. So the base of the log was 32. So this will be 32 to the x power equals 1 over 32. Perfect, Bree. Anytime you have something changing from a whole number to a fraction, that tells you it's going to be a negative exponent because it's dipping to the denominator. So this would be 32 to the negative 1 power. Therefore, my answer is negative 1. The next one, same thing. And Bree kind of, spoiler alert. Change to exponential. So 9 to the x equals 3. Some people will put 3 to the x equals 9 because they think it's always the smaller number. Don't do that. You have to follow the pattern. The base was 9. The base has to stay 9. So it's 9 to the x equals 3. Now, if it's getting smaller, that is going to be telling me that the exponent is a fraction. Remember, a fraction is really representing a root. So like 1/2 is a square root. 1/3 is a cube root. So this, the square root of 9 is 3, so this must be 9 to the 1/2 power. Therefore, the answer is 1/2. Try the last one on your own. And then we'll take a look at actually using our calculator to find the values of ones that are not rational or integer answers. What did we get for number 16? 10. No. 2. 10 to the x equals 100.
10 times 10 is
10
100.
times 10. Yes, 10 times 10 is 100, but that exponent would be 2.
Okay.
Okay. So on the back, we'll get those vocab words that I kind of already introduced. One of them, the common logarithm, is this one. It's when it has a base of 10. However, they won't write the 10. It's just assumed or implied to be there. So if you were to see, for instance, the log of 2, just says log 2. This is actually log base 10 of 2. They just don't write the 10. Okay, it's implied or assumed. Just like when we see like x by itself, we know that's really 1x. We know there's a 1 hiding there. This is the same scenario. So the base of 10 is implied. This is the type of log that you can type in the calculator. So your calculator uses base 10 automatically. And that's why it doesn't show up with a little base, it just says log. Now, a natural logarithm is going to look a little different. It'll say ln. So for example, ln of 2. This is called the natural log. The natural log is going to show up a lot in calculus. Most of the stuff that they do derivatives and limits with have natural logs instead of regular logs. And it's still an exponential function, but it has a base e. So this is actually log base e of 2. Now, what is e? Does anyone know what e is? No. It's like pi. So e is an irrational number. It's a constant. Okay, so you can think it's like pi. Okay, because pi is 3.14, et cetera, et cetera, et cetera. Goes on forever, never stops. We have a calculator button we can press to make it really accurate. E is the same or similar idea. And we can see what E actually is, or estimate it, using the calculator. So you'll notice that the E button is actually right above the divide symbol. Now be careful because there are letters, like if you press on mine, they're green. The alpha button, you'll get like just a letter E. We're looking for the number E. So we would press second and the divide symbol. And if you hit enter, it will give you the decimal approximation. Just like pi, they only show you some of the numbers that fit on the screen. So 2.718. And then just put like dot, dot, dots after. Okay. Now, if we were doing the log with a base of this number that goes on forever and ever and ever, we'd be typing in our calculators forever and ever and ever. So that's why instead of doing log base e of 2, they use the natural log. And our calculator automatically will calculate that for us. So you can see that the natural log button is right underneath the log button. So for example, if you wanted to type this in, you could and get your answer. Okay? These will be a lot of times very irrational decimals. So we will be rounding. All right, so number 17 through 20 say that we are to evaluate each logarithm, and we may use a calculator for these. So again, since this is log of 900, this is really log base 10 of 900. So you could try doing it by hand if you want to. If we're evaluating this by hand, I would set this equal to x. I would then change it to exponential form, which is 10 to the x equals 900. And then I hit a roadblock. 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. So like I don't know a number that's a whole number that I can plug in and get 900. Okay. So at this point I would want to say let's use the calculator. Now to use the calculator, you're just going to type in the original equation, log, or expression I should say, log 900. And you can see it doesn't come out to be a whole number. So we're asked to round to the nearest thousandths place, which some of you have trouble with rounding. Thousandths place is 3 spaces out. To round this properly, we look to the number directly after it, which is 2. If it's 5 or above, we raise it. If it's 4 or below, we drop it off. So it should just be 2.954. A lot of you lose half points on quizzes and tests for rounding. So be careful. Next one says the natural log of e. So in our calculator, if we want to do it in there, since they said we can, natural log of e. So we have to go find the e button, second, our divide symbol. Since you're not putting anything after, you don't have to close the parentheses, but if you want to, you can. And we'll just get 1. Now technically, if you're rounding to the nearest 100,000th, you should still put the zeros, but I probably would not mark off for that. The next one, natural log of negative 1.87. Uh-oh, error, non-real answer. When you get this error, that means that it is undefined at this point. Now, let me show you why algebraically. If we were to rewrite this and try to do it by hand, remember the natural log is really log base e. So log base e of negative 1.87. Now to evaluate this by hand, we would set it equal to something unknown, x. Then we would change to exponential form. E to the x equals negative 1.87. Now the reason that this is undefined is that no matter what number I were to plug in for x, let's say e to the negative 2, I would end up with 1 over e to the positive 2. And e, as we found, is this number, 2.71e, etc. If you square that, 1 over that number is still positive. It's a small fraction, but it's still positive. So no matter what number you plug in, you're never going to get it equal to a negative number. It's going to get very small, but never negative. Okay? So when you're raising something to the x power, it cannot be negative. Because all it's going to do when it goes into the negative is get very, 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 very small. So if this number can't be negative, then the number we're taking the log of can't be negative either. Otherwise, we're going to get an undefined answer. When we see the graph down here, that will make sense. Now, number 20. Go to try to put this in my calculator. And it's log base 2. My calculator only does the common log base 10. So we can't use the calculator because it is not base 10. So this one has to be done manually or by hand. Set this equal to a variable, x, change to exponential, 2 to the x power equals 16, and then ask yourself 2 to what power is 16? And we will get 4. Again, later on in the chapter, I will teach you a formula that will allow you to use the calculator to change the base. It's actually longer to type it in the calculator than it is to just do this with the change of base formula. All right, last thing we're going to do is we're going to graph a logarithmic function. So here's an example of one. I think it got cut off a little bit on your paper, so I apologize. But here are the original function, which is y equals 10 to the x, which we graphed those last week, right? Exponential growth. The logarithmic function is its inverse. So if you remember, the inverse is reflected across the line y equals x. Okay? So if we want to graph a logarithmic function, we're actually going to use the fact that it is an inverse, and then you can either reflect it across the line graphically, or you can change the x and y in your table and then plot them, okay, which is what I suggest. So the first thing we're going to do down here to graph this is we're going to find the inverse. Remember, to find an inverse function, we're going to switch x and y. So this would become x equals log base 2 of y. Then we're going to change this to exponential. That way it's in the form y equals. So this would be the base is 2, so the base stays 2. The other side becomes my exponent, so this would be 2 to the x equals y. Or y equals 2 to the x. Make sure you changed your x and your y first before you start doing that. Otherwise we'll get 2 to the y equals x. And we want its inverse function. Okay? Then we're going to create a table of values. Again, we can pick any numbers. We probably just want a couple negatives, a couple positives. So let's do negative 2, negative 1, 0, 1, and 2. Maybe 3 too. So plugging these in, 2 to the negative 2 power would become 1 over 2 to the positive 2 power, which is 1/4. 2 to the negative 1 is 1 over 2 to the positive 1, so that's 1/2. 2 to the 0 power is 1. Anything with the 0 power is 1. And then 2 to the first is 2, 4, and 8. Just plugging in 2 to the second and 2 to the third. Okay, so this is for the graph y equals 2 to the x power. Now, to find the logarithmic, we're going to switch the x and y coordinates to find the logarithmic points. Because remember, inverse functions just interchange the domain and range. So, to find the logarithmic, we're going to switch those. The new one will become x and y equals log base 2 of x, which is what we're asked to graph. So we switch these. This will be 1/4, comma, -2. 1/2, -1. 1, 0. 2, 1, 4, 2, and 3. Since they asked us only to graph this function, these are the only points you need to plot. Now, if you prefer, you could have plotted these and then reflected each point across the line y equals x, which some of you like to do. We'll go ahead and plot these. 1/4, -2, half, -1, 1, 0, 2, 1, 4, 2, 3. Okay, now what you're going to notice is this is going to get really close to the y-axis. Just like how the exponential curves never touch the x-axis, the logarithmic functions are never going to hit the y-axis. So you don't want to show it going past that y-axis. It's just going to get very, very small, but never negative. Now, if you wanted to graph the other one, you could also graph that one. Just if you want to graph both, make sure you label them. But this is not required. But you can see that they have been reflected across the line, y equals x. So these points have just been reflected across that line. So for any of you visual people. See if you guys can complete the 2 closures. And then your homework is the worksheet you picked up on the way in. You can tell me what they got for part A, writing it in logarithmic form. Should be log base something of something equals something. What do we got? Brett, what'd you get? Log base
2, 32 equals 5.
Perfect. And then how about B? Jaden?
X equals
X equals what?
3.
3. Perfect. And we get 4 to the x power equals 64. And then you just have to test it. 4 squared is 16. 4 cubed is 64. Okay, so these types of questions could be on your no calculator part, so make sure you are familiar with your powers leading up to that quiz.